I'm going to speak about a joint work with Marcelo Alves and Desislava Kushlukova. Marcelo Alves is from Curitiba, Federal University of Paraná, Brazil, and Desislava from Campinas, from State University of Campinas. The work is based on cohomology related to partial group algebra. So I will start with some definitions. So the key definition is that of a partial representation of a group. Can you see my screen?
Yes, yes.
Yes.
Okay, thank you. So a partial representation of a group G into a unital algebra A is a map, a pi, such that the following three properties are satisfied. I would say it respects the product if you multiply if you have this factor on both sides as kind of witness, so it's pi of the inverse of G, and then you can respect product in this sense. Or symmetrically, if you have the inverse pi of the inverse of H on the right hand side on both sides of the equality, then it respects products. And also it is unital in the sense that it sends the unit element of G into the unit element of algebra. If you take any group, ascend 1 to 1 and all other elements of G into 0, it will be a partial representation. It's easy to see. So there are plenty of partial representations, and they appeared in the theory of sister algebras in the papers, one by John Kyiv and Jan Rieben, and another one by Rui Axel. Applications were found for important classes of sister algebras, and out of the theory, beside the theory of sister algebras, for graded algebras over fields, for Hecke algebras over fields of characteristic 0, and some interesting developments were obtained for Hopf algebras. So the notion was extended for partial representations of Hopf algebras, and there are interesting papers around that. So we study structures of partial representations. The first paper was by in joint paper with Rui Axel and Paulo. We studied partial representations for finite groups, mainly for finite group G, obtaining some structures, structure results, and then for arbitrary groups G, with a joint paper with Natalia Zhukavets on finite dimensional representations of arbitrary groups. In the paper with Axel and Piccioni, we introduced the concept of a partial group algebra, which I will recall below. And this is an algebra which is responsible for partial representations of a group G in a similar way as the usual group algebra is responsible for for usual representations of the group. Further investigations were made on partial group algebras in a joint paper with Cesar Posinomilis, and then in two joint papers with Juan Jacobo Simon. With Juan Jacobo Simon, we studied mainly, we concentrated mainly on the isomorphism problem of partial group algebras, asking the following question: if you have two groups and their partial group algebras are isomorphic over some field, can you say that the groups are isomorphic? So an interesting example was constructed by Axel which, well, it's an easy example, but it was observed by Excel first, that if you take the cyclic group of order 4 and the Klein group, which is also of order 4, then their partial group algebras are not isomorphic over the complex numbers. So that's contrary to the ordinary group algebras, which for finite abelian groups remember only over the complex numbers, remember only the orders. So while the ordinary group algebras are isomorphic, for the cyclic group of order 4 and the Klein 4 group, then the partial group algebras are not isomorphic. So there is a separate team of working on that, but the isomorphism problem is not true. There are counterexamples and so on. But this is not really, as I'm mentioning, only by the way. So what is the partial group algebra? First of all, we recall the a semigroup defined by Excel in his paper published in Proceedings of IMS in 1998. So given an arbitrary group, we define a semigroup by generators and relations. To each group element G, we take a generator. And so we require the following relations. So these relations come from the definition of partial representation. So you see again that if you have this witness here, the inverse of G, then you can glue together G and H, or symmetrically the inverse of H from the right-hand side, then you can glue together G and H again. Also, it respects the identity element. So it's going to be a monoid. Excel proved that this is an inverse semigroup. And then in a later paper, Kellendon-Lawson proved using a result by Maria Sendri that this semigroup is indeed isomorphic to a known construction called the Bejerus prefix expansion of G. And so this fact is used when we're dealing with partial representations in an important way. So then the partial group algebra is the semigroup algebra of the semigroup over a field K. It could be over a commutative ring also. So it follows directly from the definition of Excel semigroup that this map is a partial representation. And the partial group algebra has the following universal property. For any partial representation pi of G into some unital algebra A, there is a unique usual representation of the partial group algebra pi tilde, such that this diagram commutes. So it factors through this map, which maps G into the generator of the partial group algebra. Partial representations are strongly related to another concept called partial action. Well, there are related notions called partial actions, and we are working with the notion in the sense of Excel. And without specific names or with some other names, they appeared in other areas also before independently. For instance, when dealing with semigroups, partial actions are there without the specific name. And another example is differential geometry under the name of maximal local action. A local action are related to partial ones, but maybe I mentioned when I show the definition. So there are applications usually in the theory of sister algebras, applications of partial representations come together with partial actions. So we can say that those examples in which those cases in which we have applications of partial representation to sister algebras, we have also applications of partial actions, and they are introduced in the theory of sister algebra by actions in order to endow important classes of sister algebras by by a structure of a more general cross products by partial actions. We can find the general definition of a partial action by papers of XIII. The abstract definition of a partial action of a group on a set could be found in the paper of 1998 mentioned above, but also for sister algebras, there is an important concept of a twisted continuous partial action of a locally compact group on a sister algebra. It's also in a paper by XIII. So besides the sister algebras, applications of partial actions were found to graded algebras, to Hecke algebras, to paradoxical decompositions, to shifts, topological higher rank graphs, inverse semigroups, restriction semigroups, Leavitt-Pass algebras, Steinberg algebras associated to ample topological groupoids. In particular, Hecke algebras over fields of characteristic zero are shown to be cross products by twisted partial actions. Also, Leavitt-Pass algebras and Steinberg algebras are shown to be skew group algebras by partial actions. So what is a partial action? A partial action alpha of a group G on a set consists of a family of bijections between subsets. So the domain of alpha G we denote by dg inverse and the range by dg. So these are bijections, also called partial bijections, such that the following properties are satisfied. The partial bijection related to the identity element is just the identity bijection of X, so identity permutation of X. Property 2, the composition of alpha H with alpha G is a restriction of alpha GH. So if you have a usual action, then this composition just equals to alpha GH, but in partial case, it's only a restriction. And what is the composition of partial maps? It is the same as defined, for example, in the theory of semigroups, inverse semigroups, when we consider the symmetric inverse semigroup of a set. It consists of all partial bijections of a set with respect to the composition on the largest possible domain. Now, if X has some additional structure like a topological space, then the domains are assumed to be open sets and the bijections are continuous. If X is a semigroup or an algebra, then we assume that each domain is an ideal, two-sided ideal, and each alpha G is an isomorphism. In this case of semigroups or algebras, there is a class of partial actions which is important for us. This case when each ideal xg is generated by a central idempotent. So in this case, we say that the partial action is a unital partial action. So each xg is a unital algebra or unital semigroup, a monoid. So two homology theories related to Abel motions were introduced. The first one was introduced in a joint paper with Mykola Hripchenko, published in 2015. And it is based on partial actions. So the modules, instead of being abelian groups on which group G X usually, we take commutative semigroups on which GX partially. Then we relate this cohomology to partial projective representations, and also study interpretations in terms of extensions. So we have two more papers with Mykola in 2017, 2018, also a paper with Mykola and Mayumi Makuta, published in 2020 about the third cohomology group, partial cohomology group, and also a paper with Mykola Kripchenko and Juan Jacobo Simon, in which we study the globalization problem of partial cohomologies when the module is an algebra, so when we have a partial action on an algebra. There is another cohomology theory which has surprisingly not much relation to the first one. Surprisingly, because partial actions and partial representations are strongly related, but they define partial cohomology based on partial representations. And this cohomology is the topic of my talk. It was introduced in a paper by Edson Alvarez, Marcelo Alves, and Maria Julia Redondo. So the starting points, as I mentioned, in the first year, the starting point are partial G modules, which are partial actions on commutative semigroups. The reason which we introduce this way with Mykola is that in particular, it fits Excel's general concept of a twisted partial action of a group, and also it serves partial projective representations, which were introduced in joint paper with Boris Novikov and further studied with Boris Novikov in other papers, and also with other authors, Hector Pinedo, Elder Lima. So there are several papers on partial projective representations, and also a paper, my paper with Nicola Sambonet on partial projective representations, which use that kind of cohomology. And also that cohomology with Mykola based on partial actions also used in a recent paper, a recent series of two papers with Antonio Paques, Hector Pinedo, the first one, in which, so in sequence of two papers, we give a partial action version of a so-called Chase-Harrison-Rosenberg 7-term exact sequence related to, their sequence is related to a Galois extension of commutative rings, and this more general is related to a partial Galois extension of commutative rings. Partial Galois extensions we defined, introduced and studied in earlier paper of 2007 with Miguel Ferreiro, Antonio Paques. And now in a sequence of two papers, we give a Chase-Harrison-Rosenberg sequence. First paper with three authors, including myself, Antonio Paques, and Hector Pinedo, and the second one with four authors, also including my ex-student Itael Mahosh. This cohomology was, that cohomology, the first one was also extended to Hopf algebras, and also appeared in study of ideals of reduced cross products of sister algebras. Now, with respect to the second theory, which is of Alvarez Alves Redondo, the partial G modules are modules over the partial group algebra. So this is also very natural. And partial modules over partial group algebra we studied where we study structure of partial representations. So it's based on partial representations or on vector spaces or free modules over a commutative ring, if we want a commutative ring. So how it is defined? So given a partial representation pi, we consider the elements E sub G of the form
pi g times pi g inverse. So it is known and easy to see that they commute, these elements commute between themselves. So we can generate a commutative subalgebra by these elements, let's denote it by B. And then we can define a partial representation by endomorphism on B, or K endomorphism of B. K could be a field or more generally commutative ring this way. So then it can be shown that it's a partial representation, transforming B into left module over the partial group algebra. Then we can we consider an augmentation map epsilon, which is a epimorphism of left modules over the partial group algebra defined this way. So any element S of the partial group algebra is mapped to S times S inverse. Now, this S inverse has to be explained. So is it invertible? Actually, we take we can take a certain kind of involution. So it is better to correct this a little bit in order to let's take only the generators. So, and the S inverse means then G inverse. So since the XIII semigroup, so the partial, let's recall the partial group algebra is just the semigroup algebra of XIII semigroup, and XIII semigroup is an inverse semigroup. So this inverse in the sense of inverses in inverse semigroups. So we can consider the augmented ring, okay, with this augmentation map, and define cohomology of this augmented ring with values in arbitrary left module over the partial group algebra. So in a well-known way, so more specifically, the nth partial cohomology group then will be the x, the right functor of the Hom functor, okay. And now in that paper by Edson Alvarez, Marcelo Alves, and Maria Julia Redondo, they study this cohomology. In particular, they study the Hochschild cohomology of the partial skew group algebra. So I'm not giving the definition of what is a partial group algebra because of lack of time, and I don't need it really, but I just mentioned by the way, so given a partial action of group on an algebra, I can define the partial skew group algebra. So they study the Hochschild cohomology related to, so they they prove the existence of a spectral sequence relating the Hochschild cohomology of the partial skew group ring with partial group cohomology and the Hochschild cohomology of A. Analogously, we may end of B with the structure of a right module. So this is just symmetric. The question where you put the G inverse. So if you put symmetrically, you get the right module. And we can define also partial homology groups, okay, as a Tor function, the right function of the tensor product. These values in a left K part G module. So let me give our main result. So theorem A. Let G be an arbitrary group and V be an irreducible or indecomposable left module of the partial group algebra, which is finite dimensional over the field K. Then there exists a subgroup H of G and an irreducible or indecomposable module U over the group algebra KH. Now this is just a usual group algebra KH, such that the partial cohomologies with values in V are isomorphic. These cohomology groups, sorry,
homology. There is homology and cohomology. So these homology groups are isomorphic to the usual homology group of H with the values in U. And the same is true for partial cohomologies. So the partial cohomology group Hn is isomorphic to the usual cohomology group of H with values in U. Now, I'm recalling that in that paper with excellent Piccioni of 2000, in order to get some structural result on the partial group algebra for finite groups, we shown that the partial group algebra is isomorphic to, if G is finite, okay, is isomorphic to a groupoid algebra, where gamma G is a groupoid associated with G. So with using this groupoid, we get a corollary for finite groups. So if G is finite, then each partial homology group is isomorphic to this direct sum of ordinary homology groups HK, where the sum is taken over the connected components delta of this groupoid gamma G, and H is an isotropic group of some vertex of delta. And also the same holds for cohomology groups. So we can define also the partial cohomological dimension as the projective dimension of B considered as a left module of the partial group algebra. So more specifically is the maximum I such that H, the ith cohomology group is non-trivial for some V, for some K par G module V. Recall that this is analogous to the case of usual cohomological dimension, which is related to the trivial module. Okay, so in this, which is a projective dimension of the trivial module, K considered as a trivial module. So in this theory, we consider B, that B as kind of trivial module. It's not trivial. The action is not trivial, but we put it in the place of the trivial module. Okay, so corollary C, we prove that the partial cohomological dimension of G is greater or equal as the usual cohomological dimension of G. And we conjecture actually that they are equal, but we can show it for groups which are not torsion-free, because in that case, we know that the ordinary, the usual cohomological dimension is infinite. So we show that this equality for the case if G is not torsion-free, but in general we don't know. And another conjecture is about the augmentation ideal, which is the, well, not ideal module. So it's the kernel of the augmentation map. It's one-sided ideal, okay, ideal, but one-sided ideal. If G is so we conjecture if G is a free group, and then we conjecture that this kernel of the augmentation map is a projective module of the partial group algebra. If we are able to prove it for infinite cyclic group. Okay, so this is roughly our results, which actually are more precise. More information we have, more facts, but this is a simplified, the essence of our results. So thank you for your attention.
Thank you, Professor Dokuchaev. Are there any questions? No? Thank you again. Yes, please stop sharing your presentation.
Yes.